Hello everyone, welcome to this online course on material science. This is lecture 9 in the module 1 on magnetism. If you recall, in the last couple of lectures, I tried to introduce the basic concepts in the quantum mechanical framework to understand magnetism, right? I started talking about the state of a system, and I said the system can be anything like as simple as an electron moving in the free space, or it could be like more complex, like tens of electrons in an atom, right? Or it could be a piece of solid. There are a lot of complicated things going around. So depending on the problem at hand, the system will vary, but the idea is that the system will be denoted by some ket vector denoted by this curly bracket, right? And we can put some label inside to denote the name of the ket, right? So it's a psi ket. So in the diamagnetic discussion, we will see this important state that will be considered is known as the ground state of the electron, right? And we put 0 to denote the ground state. So idea is that the ground state is a state where the system has a minimum amount of energy, right? That's the ground state. And then we talk about another kind of vector which is known as the bra vector corresponding to each ket. So if this is a ket vector, then corresponding to this, we will have a bra vector, which is denoted by a curly angular bracket pointing the other way, right? And so once we have a pair of like ket and the bra vectors in our hand, the next point is that can we define an inner product between them? And the way to define an inner product, let's say we have two vectors. One is like the ground state of the electron as a ket vector, and we also form a bra vector from this ket, right? Then the inner product between these two vectors is defined as we put the bra on the left and then we put the ket on the right, right? So this is a notation for the inner product, and this will produce us a number. And we say that if you want to know the wave function of this ground state, what you need to do, you need to perform the inner product with the position bra vector. That will give you the wave function form of this ground state, right? So that's another concept, very important for us. Now, I also mentioned that usually in quantum mechanics, the measurable quantities are denoted by operators, right? For example, you can measure the energy of the system. So the energy will have an operator in quantum mechanics, and usually we put a hat to denote that this is an operator. And the important question to ask that how this operator operates on some vector, right? Because what operators do actually, they operate on some vector. In the context of diamagnetism, we will see that this sort of operator usually will operate on the ground state of the electron, right? So this is the ket vector, and that's an operator. And by this, I mean the energy operator is operating on the ground state. We will see these things coming in the diamagnetic discussion soon. So operator operates on the ground state, and it will produce some other, I don't know, some other state. Let's say some other state. But the important point is that this operator by itself does not carry any value in this raw form, right? In this form. Then the question is, how do we define the value of the operator, right? For example, if this is an energy operator, one might ask, what is the value of the energy in this state, the ground state? Then we say that we need to perform the expectation value of that operator. That's really very important concept. And the way you find out the expectation value of any operator is that you have to know two things. One is the state you are talking about and the operator itself. In the diamagnetic context, let's say, for example, we know the energy operator, which is usually not denoted by E hat, rather we say that it's the Hamiltonian operator, right? So we are trying to find out the energy of a system, and our operator is the Hamiltonian operator. How do we form an expectation value in the ground state of the electrons. So we said that you have to put this operator between a ket and the corresponding bra, right? So that's the expectation value of the operator H in the ground state, denoted by this ket and this bra, right? And we also said that this is nothing but a number, right? And can we see that? Yes, of course, because H, when operating on this ket, will give you some ket, right? And then that ket will be, so let's say this is some ket, maybe a 0 prime, just to make it clearer, right? And then on the left side we have another bra, right? So this is an inner product, it has to be a number. And we also said all this expectation value is just an integral, right? So you have to perform the integration. And the rule is that you think about, you ask yourself first, what is the bra vector and what is the wave function corresponding to that bra vector, right? Then you ask what is your operator, then you ask what is the wave function related with your ket vector, and then you perform the integration. Let's assume that for this ket we have some wave function, so let's say psi 0, which is a function of r, right? So that's the ket on the right. Then we will have the operator operating on this function, and then we will put the wave function corresponding to this bra vector, right? And we always say that if the ket is the psi naught r, then the bra will be the complex conjugate of this wave function, right? So we have these three things, and then we need to perform the integration over the whole space, and that's the expectation value of some operator, right? Okay, and another very important concept that I introduced, I think, in the last lecture is about the commutation of the operator. And I said that usually you define this operator between two vectors. So for example, we have some operator, let's say x hat. This is the position operator, right? And we have another operator which is the px, the momentum along x. That's also an operator, right? And the way we define this operator is that you have to put the operators in this order first, and then you put the reverse order, right? That's how we define an operator between two. That's how we define a commutation relation between two operators. And we have specified that the important point to note is that if this is not equal to 0, then we say x and px do not commute with each other. It means you cannot change their order. You have to be careful. So xpx is not equal to pxx, right? Because they don't commute. But I have mentioned some other relation like y, right? It's the state of a particle moving along, say, y, right? And we have some momentum along x. They are not canonical conjugate, right? So their commutation is 0. All that means is that actually you can see it from here, the ypx minus pxy is 0. It means ypx is equal to pxy. So you can change the order. You don't have to worry about that. The important message here, in the diamagnetic calculation, we will see there are some operators and we need to change their order. But before doing that, you always, in quantum mechanics, ask, and you have to be careful whether the operators you are changing in order, whether they're commuting or not commuting. If they don't commute, you have to be really careful, right? That's the central point we need to bear in our mind. And this basic concept once we have, now let us start our discussion on the diamagnetism using a different approach from the classical one, right? And my plan here is to start from the materials perspective, right? So let's ask first, what type of materials usually diamagnetism can be seen, right? The answer is, it turns out all the materials we have, they have some degrees of diamagnetism inside them, but it could be weak. And by diamagnetism, we mean it's negative susceptibility, right? We know that for diamagnetic material, the susceptibility is always negative. And the question is then, if it is too weak, or maybe it's not strong enough to beat the other type of magnetism. Because if you remember in last, I think maybe few lectures back, I mentioned that different types of magnetism can coexist in a material. Now the question is, let's say we have diamagnetic effect and also some other paramagnetic effect. It turns out usually the case that under some situation the paramagnetic strength wins, and then the material becomes paramagnetism, right? So the important point here is that to observe diamagnetism in some material, it is good that we understand that what type of element usually show diamagnetic behavior. Let's say we start with some noble gases like helium, argon, neon, krypton, xenon, right? We have some alkali halides, sodium chloride, potassium chloride. We can think of a molecule also, right? So it's nitrogen molecule. It turns out these are diamagnetic. And the reason, if you look at them a bit carefully, all of them has field shell configuration, right? It means they have 2n square, right? You already know from your, I don't know, first year physics that in the first energy level there are 2 electrons at most, and then there are 8 electrons, right? So if the electronic shells are filled according to this law, these are field shell configuration, right? And to understand or to see the diamagnetic effect, it turns out the atoms has to be atoms or the ions, it doesn't matter. For example, if sodium plus, right, it means it's you strip up one of the electrons. So the ion itself is a closed shell configuration. So whether it's atom or whether like a noble gas or whether it's like an ion, the central point is that to observe diamagnetism, the atom or the ion should be in the field shell configuration. So this condition usually is good to study the diamagnetism, right? Diamagnetism. But you will see in the lectures to come in future, right, that if you don't have a field shell configuration, then very different behavior can occur, right? And usually this can be explained in the context of paramagnetism. So paramagnet, right? And one important thing is to know is that in this field shell configuration, right, suppose we are considering the ground state of the electron, and we know how to denote it, right, with the sket vector where 0 is the label. So let's have a look at this expression. This is the real 0, right, the value 0, and this is the label 0. It says this L, I have introduced this operator in last lecture. I'd say this is the angular momentum operator, which is a vector operator. So this statement is saying that if you have a field shell configuration, then if the angular orbital momentum operator operates on the ground state of the electron, it will produce 0. So the meaning of this line is that if for a closed shell configuration in the ground state of the system does not have any net angular momentum. That's a very important point to remember, and that's a quantum mechanical statement. You can see it's very difficult to understand how this can be in the classical physics picture, right? Let me comment a thing here. Usually in classical physics, we always try to understand things like having a picture in our mind, right? And the reason why we are used to with this sort of ideas, because in our education system, right, we always introduced with the classical physics first, and then at some higher level we introduce the concept of quantum mechanics. It is as though we are trying to say nature is very classical, and then at some level you need quantum mechanics, right? But let me tell you something, this is quite opposite, right? In reality, nature is fully quantum mechanical, and it appears to us like a classical at some level. So depending on your exposure to classical physics, this statement can be quite counterintuitive. But in quantum mechanics, this can be explained, but I don't want to go to that discussion here because it requires a bit advanced formalism. But the rule is to remember for diamagnetic discussion that for diamagnetism we will consider field-shelled atoms, and in that field-shelled atoms, if the electrons are in the ground state, then there will be no net angular momentum, right? That's the message I want to get across. And then I just want to finish up this lecture by showing you some data, right? This is from this classic book of solid-state physics. I hope every one of you heard about this book. This is the classic old one from Ashcroft and Marmin. You can see there are different ions here, the noble gases here, different ions there, and you can see the value of susceptibilities here. So these are all susceptibilities, and I believe the unit is centimeter cube per mole. And yes, so this is the unit in which these data are given, right? You can see, you can derive this or experimentally measure the diamagnetic susceptibilities of this material. And I want to finish by just showing you this graph from this Stephen Blundell's book, where you can kind of plot, right, the susceptibility. Here they are presented data in meter cube per mole unit, and they are plotting it against this ZEF R square. So let me comment on that unit. So ZEF is, I would say, the number of electrons in ion, and that's an effective number. We will see why it's called effective number. That's an effective number of electrons in that ion you're considering. And R square is some sort of, you can see it's like a shape, right? So 4 pi R square is like a surface area of that ion. So R square is the radius square. So it's kind of giving you the size of the atom, right? It's giving you some information about the size of your ion, size of the ion. So once you have the number of electrons and the estimate of your size of your ions, then you can see this data, right? Like here we have magnesium ion, here we have sodium, then calcium, over here we have lithium. So it's kind of going up as this value is increasing, right? So number of electrons and the shape of the ions scales with the susceptibility, right? So, and we will derive this equation, which clearly will tell us how this ZEF R square is related with the susceptibility, right? I think that's about it, and I want to give you these references, right? And this is the magnetism in condensed matter with the Blundell. This is the graph I've taken from this book, and we have this classic, right, from Stephen Simon, the Oxford series, and then the solid-state physics from Ashcroft and Marmin, right? Yes, I think that's about it. And in the next lecture, I'll be start talking about how to derive the expression for diamagnetism in a quantum mechanical setup, okay? And I think that's about it, and thanks for listening.